Hello, my name is Lindsay Burke, and I was a propulsion design engineer.
Hi, my name is Samantha Montalbine, and I was the mechanical design engineer.
Hi, I'm Mark Nyevgen, and I was also the mechanical design engineer. We're students at the New Jersey Institute of Technology taking ENGR 423, the Drone Science and Fundamentals course, where we designed our drone.
This is the Pelidrone. It is a purely waterproof drone that is designed to be able to fly over bodies of water and be able to be retrieved in the circumstances that it might fall and fail.
One of the main limitations that drones face today is limited flight times. The current state of lithium batteries severely restricts the flight time capabilities of drones, often limiting it to less than 10 minutes. And so what our drone allows is us to land on water in order to conserve energy and extend our flight duration.
We did this by designing a positively buoyant drone body, which allows it to float on top of the water.
And in these circumstances, it allows that if it is to fail, we can find it on the surface of the water and be able to retrieve it.
When we evaluated the propulsion system of our drone, we needed to make sure that our motors had ample thrust. And so what the thrust allows our drone to do is it allows it to counteract the force of gravity in order to produce lift.
And in the case that the drone is completely submerged, we incorporated a gasket to our design so it's fully waterproof, protecting all of the electronic equipment.
And beyond just the gasket, we were able to take on and off so we can access the battery and all the critical components. We also used a unibody design so that there are minimal openings so that as little water as possible can seep in the event of failure, while also making sure that everything is safe on the inside so that the body can sit on the surface of the water and wait to be retrieved safely. We were able to successfully design the drone such that it can be waterproof and sustain these typically unusual conditions that drones can't fly in.
Many commercially available drones do not have such technologies in order to survive through these harsh conditions, so this is where our drone really stands out.
And it stands out in its broader applications in the defense industry, weather surveying, and in general research applications. Waterproof drones are vital for national defense and strategic deterrence, specifically enhancing the capabilities of submarine fleets. These drones enable crucial reconnaissance and situational awareness while the main vessel remains hidden, preserving critical stealth. However, current drone prototypes are often cost-prohibitive and utilize complex, custom-made components. These parts are impractical to store, repair, or replace within a submarine's confined, resource-limited environment. We address this issue through 3D printed components. This technology allows for the rapid, on-demand fabrication of critical parts directly aboard the vessel, transforming the drone into a sustainable, adaptable tool that maximizes operational readiness. Waterproof drones offer a crucial application in weather surveying. Modern weather models are complex, requiring massive amounts of data and specific information, especially concerning storm dynamics. This critical data is currently gathered by manned aircraft, an incredibly risky operation that endangers the lives of pilots and scientists. We plan to mitigate this risk by using a specialized waterproof drone. If storm conditions become too severe, the drone can simply land on the water and safely float until the weather subsides. This capability eliminates human risk while ensuring continuous data collection, vastly improving the accuracy and safety of meteorological research and forecasting. Waterproof drones are a critical tool in research, and another important field is surveying drinking water quality. Traditional sampling is often labor-intensive and limited to accessible areas, which means large reservoirs or remote sources are monitored infrequently. The innovative use of a drone allows for a single operator to collect real-time, high-resolution data or physical water samples from virtually any location.
One of the most valuable learning resources for completing this project was my experience with the NJIT SAE Aero Design team. I've been a part of this team for the last 4 years of undergrad, 3 of which I've served as the electronics and propulsion team lead. So through this experience, I was able to inform our drone design. So I was able to calculate the thrust output of our motors, which was approximately 1.6 pounds force. So from this, I was able to figure out what the maximum weight of our drone should be in order to achieve an appropriate thrust-to-weight ratio. The thrust-to-weight ratio should be approximately 2 to 1, which means that the thrust needs to be double the amount of our weight. And so if this thrust-to-weight ratio is not achieved, our drone will not be able to maintain a hover efficiently. So We calculated that with a drone that weighs approximately 2.5 pounds, our thrust to weight ratio will be about 3, which this will provide us with ample efficiency in order to fly our drone safely and effectively.
The most important learning resources we used throughout this project were our classes at NJIT. For the buoyancy calculations, we used basic principles from our fluid mechanics class. We were then able to design our drone body with these equations in mind and then validate them in SolidWorks to ensure that it met our weight criteria. We also used our ME 430 class, which is our introduction to computer-aided design class, to design the whole drone in SolidWorks and as well as the gasket, all so it can be prepared for laser cutting and 3D printing.
In addition, something that we took into consideration with our designing was our capstone courses in ME 430, which is our computer-aided design course here at NJIT. We put a lot of thought and effort into making a unibody for the body, as we'll discuss more later. When creating the model, we put a lot of consideration in the DFMA, or design for manufacturability and assembly, as well as a lot of design techniques such as configurations and global variables to make sure that we can design this drone as efficiently as possible. So a lot of design choices that we made were with our goal of making it very affordable, as a lot of the current drones in the market that serve this purpose are a bit expensive. So some of the considerations we made were using our local makerspace in order to laser cut, 3D print, and assemble the majority of our drone. Beyond decreasing the amount of assembly time required, which adds to the cost of the project for making several parts to the body, one of the main factors in choosing a unibody form for the drone was that we can make sure that it's as waterproof as possible with minimal effort, so that the only real holes that are exposed to having any leaks are the holes for the motor wires to go in, as well as the top gasket assembly, which we are very easy to take on and off and make sure that it's sealed.
After our preliminary design, we took further steps to optimize our design to improve its weight efficiency and also to minimize the cost and to minimize the amount of material. Another important thing to consider is optimizing our design for the resources we have, specifically the types of printers we have at the makerspace. So we were able to minimize the overall size of the drone body to fit on the Prusa XL printers at NJIT's makerspace, and we were also able to minimize the amount of overall material in the body so we can minimize the cost of PLA used while also minimizing the total weight.
So one of the factors we had to take into consideration was the arm length of our drone. So the propellers are each 9 inches in diameter, which means that we can't have the propeller clipping into any part of our drone body. So this meant that we needed to have some sort of buffer in between each propeller so that they don't make contact with each other. And as such, we decided on a standard 2-inch difference between the propellers. And so what this meant was that we needed to create some sort of wire extensions so that we could extend the wires from the motor to our ESCs, which were located in the central body of our drone. And so to create this, we used wires and we soldered bullet connectors to each of them in order to extend the wires and create a design that was easy to take apart.
So in the past, I've had a lot of experience with mechanical design as I've served as a design engineering intern for 3 internships now, but I haven't been able to delve too much into electronics. So I really anticipated learning a lot from my group mates who had more experience than me in those fields, and kind of learning about things like we'll talk about later, like wire shorting or proper wire organization, which are things that I kind of knew going into it that I didn't know too much about. Also, I've never had experience with drones in the past either, and I've always wanted to learn, so I definitely anticipated needing some help with just the general kind of topics and physics behind drones beyond what we learned in the classroom.
So one thing that I wanted to learn from this class was more so about the mechanical aspect, and as a computer science major who has more experience with electronics and UAVs, so RC planes and drones, I didn't have much background in the actual mechanical design, so CAD modeling. And so from my group mates, I was able to see the kinds of designs and decisions that they were making throughout the engineering process, which allowed me to get a lot more insight into that world. And another thing is that I learned a lot about waterproofing, not just the mechanical body of our drone, but also the electronics.
few classes at NJIT offer the opportunity to create a physical final project, and this is the first elective that I've taken to actually design some physical project at the very end. So it's one thing to be able to do all of the calculations and all the simulations, pen and paper, correctly by hand, but it's another thing to then implement this into the real world where you might experience many unanticipated design challenges or many unanticipated failures. And then how are you going to design around those failures or design around any unspecified design criteria you may not have considered when you are on SolidWorks and you have the whole catalog of every piece, every machine available, but we're really limited in the real world by what we have available to us and designing around many of our restrictions, something that we don't normally consider in class, but something that's really important when designing a product for commercial use.
So everything was going pretty swimmingly until our first test flight, where we learned a lot. As Mark said previously, in our classes, we had the opportunity to do a lot of calculations and see theoretically how things should occur in real life. But it was really neat to have our drone flip over and break like a cantilever beam, which is something we learned in strength and materials, but you don't really get to see a lot in the real world. So as you guys can see, here's a video of our drone trying to lift off and kind of flipping instead. So we're able to learn a lot about calibration of the drone in this process and kind of like taking steps back to be like, okay, what happened, assess it, and what should we do from here?
After that failure, we went back to the engineering design cycle to redesign our model to try to accommodate for this new possible failure we noticed. So to maximize the strength of the arm when it's undergoing that cantilever beam stress, we tried to maximize the thickness without also increasing the weight too much. However, doubling the size of that base plate made it much more challenging to route the wires into the body of the drone. So now we have to reconsider finding new routes to wire the drone. However, this caused a potential issue with the wires being too close to the propellers. So we were able to feed the wires through slots within the drone body to make sure the amount of wire that's outside of the drone body is minimized while also ensuring the waterproof seal.
So following our first flight test, we temporarily repaired our drone so that we can test fly it again. So during the second test flight, what we noticed was that one of the motors stopped functioning. And so you'll notice in the video that you'll see that the drone starts to yaw, which means that one of the motors is failing. So this is primarily because of the failure of an ESC, which you call burning out. And so that can be caused by two different reasons, either overcurrent or a shortage. And so we suspect that potentially the wires might have been exposed to any sort of metal or something that could have shorted the wires. And so when the ESC started smoking, it heated up our drone. All of the electronics in our drone were destroyed, and all of the motors were shorted. And so from this, this was the total failure of our drone. And so future measures that we need to take are we're going to purchase better quality ESCs. These particular ESCs that are used on this drone are rated for 20 amps continuous current, 30 amp burst. And these drone motors that we have, the 2312E DJI motors, they draw approximately 14 amps continuous at full throttle with a 9-inch propeller. And so that is somewhat cutting it close because a general rule of thumb for selecting an ESC is you want to have at least 30% higher than the continuous current draw in order to account for current bursts. And so it was even more important for our drone design because our gasket and all of our electronics are contained within this gasket and it gets very hot. And so we need to have a higher buffer for our current rating on the ESCs in order to account for that.
One of the biggest discrepancies we faced between what we anticipated and what we actually encountered was with the material selection for the gasket. We believed that this would have been a very simple and very straightforward decision. However, that was not the case. We originally chose latex, a very common polymer used in the industry, but we saw that its properties changed significantly after laser cutting and it wasn't viable for this application. So we then reached out to some of the staff at the NJIT Makerspace to determine what might be the best gasket material. They recommended for laser cutting to use Buna N, so we used a commercially purchased sheet of Buna N. However, we saw that it would burn and flake up and turn into a dark powder, really the opposite of what they were saying, how they were saying it would be really successful and perfect for this application. This shows that the properties of polymers between suppliers and between manufacturers varies drastically. So it wasn't just what material they used, but also who they purchased it from. We then spoke with other collaborators, such as other staff at NJIT or even collaborators at Brown University, who suggested that the best procedure for making such a gasket is through cutting and punching operations. So in the future, we would create special cutting dies and special stamps to ensure that we can manufacture these gaskets without laser cutting operations.
It was really cool that the first time we did a drop test in the water where we had the drone sit for various hours in a body of water in a bucket with weights on top and just kind of free floating, that the body was waterproof and without the epoxy inside, able to withstand the water from coming in on the gasket side, which is pretty neat. But kind of going back to our first test flight where we just did not anticipate the cantilever beam action that occurred. One of the biggest discrepancies that led to the failure of the first flight test was a matter of the body that we modeled on CAD versus the one we actually 3D printed. We failed to consider the fact that when you're printing the layer lines, the way it printed actually can contribute to how it fails. So because we had so little layer lines, it was very susceptible to failing in the way that it did. So that was something we definitely didn't anticipate, but it was something really great to learn. And we were able to learn a lot as well about how to best secure drones, where we had a rib there, which initially the reason that the rib did not extend through the entire motor mount was because we didn't think that we were able to screw in the fourth motor hole. But Craig, the TA for this course, was able to teach us that we only really need 3 screws to secure the motor properly. So that's something definitely in the future that we would revisit beyond just making the whole piece a lot thicker. Something I really appreciated about this project was when things went wrong. The professor frequently told us in class that everything was going too swimmingly for us and that something was bound to go wrong. And as scary as it was to, given the deadlines, try and problem solve and make the drone able to be flown and figure out how to make it the best for this course, we really did have the opportunity to learn a lot. Something I didn't even consider is that you can short the wires and not only cause the explosion that the TA had to ignite with the fire extinguisher, but also that it can contribute to the motors just not spinning at all. And I really did learn a lot about not just drones, but electronics, which has been something I've always been interested in. So I really appreciate that in the course. I'm also very proud of the actual 3D model that we made, as even though I have a lot of experience with modeling in the past, I learned a lot through making it one unibody, able to be 3D printed in one big piece, and also waterproofing it. As I've always had a fascination with making gaskets, but beyond O-rings, I've had no experience in the past. So I really was grateful for all that I learned through the chaos that was the last few weeks of this project.
Overall, I really enjoyed being able to take my previous experience with RC planes and be able to apply that to quadcopters to really expand my skill set and my knowledge. I also really enjoyed being able to work with a group of diverse skill sets and perspectives and really be able to enhance my technical skill set.
Overall, I was really proud to use many of my skills I developed at NJIT, especially my CAD skills and my engineering skills in a real-world engineering application. But I learned that not everything is like in the textbook and that a lot of unanticipated issues can arise. And one skill that I was really proud to develop was designing around unanticipation, unpredictable failures, such as what happened with our drone, and trying to make sure that our design is as robust as possible.